Good afternoon, everyone. Continuing from where we left off last week, we got as far as starting to develop ideas about how we can describe the interaction of chemical substances with each other, and that is writing a balanced equation in such a way that we can understand it. It's a universal language that all chemists understand. You write reactants on the left, products on the right, and an arrow in between showing that is the direction in which the chemical reaction is taking place. We write it in such a way that we account for everything. We have to obey the law of conservation of mass and the law of definite proportions. In writing a reaction equation, we can't artificially create new atoms of any substance, and we can't magically make atoms disappear. We write them in such a way that all atoms are accounted for, whether they occur as new chemical compounds or not. And the definite proportions part tells us that we need to write sensible chemical formulae, real compounds that really exist. And we looked at some of the ways in which we can describe the formation of chemical compounds when atoms of different elements interact, and this is done by the movement of electrons. Whether some gain an electron during a chemical process, some may lose an electron, but more often than not, we find that atoms of elements share electrons, forming covalent bonds. I'll run through this rather quickly. We did this last. We looked at how we can go about it. If we take a systematic approach to balancing a chemical equation, we know what our reactants are, we know what our products are, we just need to juggle the amounts of each of them so that we obey those two laws, the conservation of mass and the laws of definite proportion. So we're creating sensible things in the right number. So we end up with the right number of each molecule type in our balanced equation. That gives us the same number of atoms of each type on either side of the arrow. And we've done that, we throw our hands up in the air and cheer because we've balanced it. Okay? Other simple examples, the reaction of sodium and chlorine, giving sodium chloride. We discover that we need, because there are two chlorine atoms in a chlorine molecule, we need to form two sodium chloride molecules. As a consequence of that, we need to make sure we have sufficient sodiums written into our equation to account for all the sodium chloride that's been formed. We also can describe the physical state of substances in a chemical reaction. Sodium in its natural state is a solid, chlorine in its natural state is a gas, and sodium chloride, when it forms, is also a solid. So we can give a little bit of extra information when we write equations of this kind. We can say something about the physical state of reactants and products while the transition is taking place. An acid-base type reaction where we have hydrochloric acid reacting with sodium chloride. This is a classical type of chemical reaction that we'll encounter several times over the next couple of weeks. An acid-base reaction. And generally speaking, in fact in all cases, when you react an acid with a base, what we get is a salt plus water. And the salt consists of those atoms that are left over after water has been formed. Another classical type of reaction we'll be looking at is the reaction of an acid with a carbonate. It's similar to acid-base in that carbonate is a basic substance. It's the opposite of an acid, and we'll explore the definitions of acids and bases. We'll do that with Graham, I believe, sometime over the next few weeks. Discuss and explore the nature of acids and bases, how we can describe them. This particular chemical reaction gives us again water, but this time we get carbon dioxide because the carbonate ion dissociates into carbon dioxide, freeing up one of its oxygens, which goes on to form water. And the remainder, the sodium and the bromine, react together to form the salt sodium bromide. Generally what we find is when we have a monoprotic base, then we require two of those to react with a carbonate to form carbon dioxide and water, and as a consequence we get two salt molecules formed as well. So the balancing process is done in such a way that when we do something to balance an equation, then we have to check that balancing that thing does not unbalance something else accidentally. So it's a case of cross-checking, an iterative process of checking and making sure we have the right number of atoms in the right place on both sides of the equation. Most of the time it's going to be relatively straightforward. Sometimes it can be slightly more complicated. When we start looking at slightly more complicated chemical reactions, and Graham will introduce these to you, then we have to be very, very careful about how we balance things. And often the process has to go through 2 or 3 iterative steps to make sure that everything balances out. But it's all underpinned by these same principles. Checking that we obey the law of conservation of mass, and checking that we're obeying the law of definite proportions when we write our chemical formula. Now, because you're a fun-loving bunch of people, I thought it might be fun for you to try a couple yourself, just to make sure, reassure yourselves that you are okay with the concepts as I've explained them, and you're able to understand how to continually check to make sure that you're balancing things properly. Okay? Okay, simple case of balancing this time. We require 2 hydrochloric acids for every calcium hydroxide in order to have sufficient atoms of every type needed on both sides of the equation. Yep, straightforward, simple, no problems. Excellent. And we need 2 waters as well, because we double the number of hydrogens by adding a 2 to the hydrochloric acid. As a consequence, we need to make sure that we express the right number of hydrogen atoms on both sides in the formulas that we've written. Yeah? Slightly different example, but following the same principles, it should be easy enough. You said optimistic. Okay? Because we have a mismatch in the number of hydrogen atoms on both sides, originally 4 on one side and 5 on the other. If we double up the number of ammonium chloride molecules there, it gives us more hydrogen to play with. We can then have a look and see what we need to do to change things. We've now introduced 2 nitrogens into the equation, so we need to account for that by putting a 2 in front of the ammonia molecule to show that that's the number that's formed. The rest of it should be balanced because we have 1 calcium on each side now, we have 1 oxygen on each side, and we have 2 chlorines, so it looks like that one is balanced now. Do we all agree? Sure? Is this a trick question? No, it's not. So we can do things with these balanced equations. It's not just about correctly describing what's going on in a chemical reaction, but it allows us to do more than just that simplistic thing, to say A plus B gives us C plus D. It tells us some more important things. It allows us to account for all the atoms, so we're not making any mistakes. Quite an important thing in its own right, to make sure we have things properly balanced. From a practical point of view, if we were to carry out a particular chemical reaction, and we got our proportions wrong, sometimes very bad things can happen. So it's important to have a complete understanding of the balanced equation, to understand how much of each thing we need to add in order to get a complete reaction to them, and not have unfortunate side effects take place. And the other thing it does is it helps us understand the relationship between different things in the chemical equation, the relationship between reactants and products, the relationship between the reactants themselves, how many of each reactant we require in order to get a properly balanced equation. So, this brings us to a thing called the mole concept, because I'm saying we need to know how much. So what we need to have is an effective way of measuring chemical substances. As I've alluded to earlier, atoms are pretty small. And to be able to, or to want to measure out a small number of atoms, say, or molecules, would be a difficult task. But if we understand something about the way in which they interact with each other, we can start to put together ideas about how we can make physical measurements of things. So, to begin this, we need to have a look at what we mean by the balanced equation, and we need to think about it in terms of scale as well. So water, 2 hydrogens and 1 oxygen. And we can write it in terms of the atoms. And that's all well and good. But as we know, hydrogen does not exist as individual atoms, and neither does oxygen. But nevertheless, as we scale up, we still find that for however much hydrogen we take, we need to take a suitable amount of oxygen to completely react with it. In this case, it's 2 to 1 hydrogen-oxygen ratio. And we can scale up to thousands. And then we can go and look at it in terms of the real world. We can say we definitely know that hydrogen exists as a diatomic molecule, and we definitely know that oxygen does the same. So we can express it in terms of molecules and not just atoms, because that's the real world, that's the central way to do it. And the point is, no matter how we choose to represent it, one thing remains constant, and that is the stoichiometric relationship between hydrogen and oxygen on the reactant side, and the same relationship between them on the product side. So we require a ratio of 2 hydrogens to 1 oxygen in order to form water. And water itself contains 2 hydrogens and 1 oxygen. So we're maintaining the balance, maintaining the stoichiometric relationship between them. So it's always 2 to 1. And that holds true for all chemical reactions. Once you develop the idea in atomic terms, you can translate it to molecular terms and still get the same stoichiometric relationships throughout. Because atoms are small, and it's very difficult to capture a few atoms in a sensible way, we can't really count them. We can't really say we want 10,000 hydrogen atoms, so it's not 1, 2, 3. It can't be done. So we need a way in which we can measure an amount in terms of something that's tangible to us, such as a weight, and relate that weight to a specific number of atoms or molecules or ions or whatever it is we're trying to measure out. And it would be really nice if we could say that 1 gram of hydrogen contained a specific amount of hydrogen atoms or hydrogen molecules. But it's a problematic thing, because a gram of hydrogen gas is a tricky thing to weigh out. So we need to have some other measure of amount. And what we use is this idea of Avogadro's number. It was worked out a long time ago by Mr. Avogadro that a formula unit, when weighed in grams, will contain a particular number of those formula units. And he worked out as 6 point something or other times 10 to the 23. So if a sample of any chemical substance contains Avogadro's number of formula units, then we have a name for that. It's called the mole. I'm unsure if he was inspired by nature when he decided to call it mole, but nevertheless the name is stuck. And formula units are, as we express them in chemical equations, the collection of atoms in the right proportions that describe that chemical substance. Sodium, oxygen, methane, sodium bromide, whatever it is, however many atoms, we need to have the right proportions, the law of definite proportions, the right number of each type of atom in that formula. So we can relate it to a mass. And we do it in this way. We know something about our atoms and our elements. And it's the atomic number that dictates which element we're talking about. But not only does an element, or atoms in an element, have an atomic number, they have a mass number as well. The atomic number is the number of protons, which is fixed for each chemical element. But the number of neutrons that can exist in a nucleus can vary. It can't vary infinitely, but it can vary sufficiently to allow us to have different types or different flavours of atoms that are of a particular element type. Carbon consists mainly of carbon-12, that is, 6 protons and 6 neutrons in the nucleus. A small proportion, about 1.1%, exists as carbon-13, 6 protons and 7 neutrons. So a difference in mass. It's still carbon because it's got 6 protons, but the two have a different number of neutrons and hence are slightly different in terms of weight. So we can say that elements have an average mass. And we take that average mass by summing the proportions of each isotope type. And we end up with carbon. The average mass of Avogadro's number of carbon atoms is 12.011 grams. Now I know what you're thinking. There are more isotopes than just those two. The other isotopes of carbon, and they range from carbon-8, I think it is, to carbon-22. They're very, very unstable. Once you get away from a certain ratio of protons to neutrons in the nucleus, you start to get unstable nuclei, and that's where we get radioactivity from. Now, Graham's going to talk to you about radioactivity later in the semester, so you understand a bit about radioactive decay and what sorts of atoms of different types of elements will undergo decay. But we can say then that we can assign a mass value to a mole, and it relates directly to the number, or the ratio of isotopes, and it's related to the mass of carbon-12. So we can redefine our mole. We can say that a mole of any element or compound has the same number of formula units as there are atoms in 12 grams of carbon-12. Hence, that's why we can say, based on the proportions of carbon-12 and carbon-13, that the average mass of all the carbon atoms in the universe is 12.01. So we now have a way of relating a mass to an amount. So we have a mass based on carbon-12. Atomic masses are averaged over the number of isotopes and the proportions of those isotopes. But every mole, every weight based on the formula and based on the isotope ratios, contains Avogadro's number of formula units. So we have a number of things related in a particular way to a weight. So we can weigh things out then and be quite confident we know how much we're actually weighing out. So isotope ratios, I'll just put a few common ones here. There are a huge number. Some of them are not stable, some of them are. These are some of the common ones which are stable. And we can see that the relative proportions of each isotope type influences the average atomic mass of these elements. So for hydrogen, the two principal ones are hydrogen and deuterium. Carbon-12, carbon-13. Oxygen has 3 stable isotopes, giving an overall average mass of 15.999. In a lot of instances, it is feasible and probably very pragmatic not to use a lot of numbers after the decimal place. So hydrogen, we usually call it 1.01 for simplicity. Carbon, 12.01. Oxygen, probably call it 16 because it's so close. It's a thousandth of a mass unit away from being that whole number 16. But you have to be careful when you do that, because sometimes there is a closer ratio, closer to 1 to 1, with some of the elements. Chlorine is 3 to 1. Carbon 35, 75% of them are carbon 35, chlorine 35, 25% chlorine 37. So it's not really practical to round that number up. It's always better to keep it, because it shows a true reflection. The same with bromine, about 50-50 between bromine 79 and bromine 81. So you wouldn't round into one of those whole numbers, you'd use the decimal places. It's a true reflection of the mass. But where it's very close to a whole number, it's common sense and a bit sensible to round it where you can. But be very judicious in your use of rounding when you're doing these things. Don't overdo it. It can lead to some mistakes. Okay? So, I mentioned that there are certain stable isotopes and certain unstable isotopes. We can vary the number of neutrons, and we can work out the number of neutrons in a particular isotope of an element by subtracting the atomic number from the mass number for that particular isotope. And that tells us the number of neutrons. Now there's only certain ratios of neutrons to protons that allow atoms of elements to remain in a relatively stable condition. Once you deviate from that ratio, then we get unstable nuclei. Some of them are extremely unstable and are short-lived, that is, they exist for a fraction of a second before they decompose and dissociate with other things. Some have a longer lifetime. Carbon-14, the isotope we didn't really mention, and we don't include in our calculation of the average mass of carbon because it's in such a small amount naturally occurring, and because it is a radioactive substance which is undergoing decay over time. So the absolute number of them varies with time. It's a stable one, even though it's radioactive and it will decay, and it lasts on average, its half-life is around about 5,500 years, so it takes a long time to disappear. But its concentration in the real world, the real universe, changes over time, so we can't really incorporate it into our average mass for carbon. So, what we do find is that in certain parts of the periodic table, there are ratios of neutrons to protons that are stable. It's not the same right across the periodic table. For the smaller, lighter elements, up to about atomic number 20, we find that on average, the ratio of neutrons to protons is around about 1 to 1. Examples given there. Carbon, definitely 1 to 1. Carbon 12, 1 to 1. Oxygen 16, 1 to 1, same number of neutrons and protons. Carbon 13, there's one more neutron than there is protons. As a consequence, the ratio is slightly different, but it's still around about 1 to 1, 1.61 to 1. It's still in that zone of stability. There's not a huge mismatch in the numbers of neutrons to protons. As we get further into the periodic table, we find that the elements with atomic number beyond 20 up to 83, which is the highest one we have any sensible information for, then the ratio is different. There are more neutrons to protons. And the principal reason for that is the more protons you add to a nucleus, the more positively charged things you capture into a tight space that is a nucleus, then the repulsion between them becomes greater. So more neutrons are required to act as a sort of glue, to hold these protons together in the nucleus and not allow them to burst out and fly off. And so the ratio of neutrons to protons increases to about 1.5 to 1. So about 1.5 times the number of neutrons as there are protons. This allows us to capture this in a particular way. We can plot a graph, and we can describe in that graph what we call the belt of nuclear stability. So we can describe the ratios from real-world information that are stable for different atoms, different isotopes of different elements. And we can see in the lower part of the graph, up to about 20 on the x-axis, then the relationship between neutrons and protons is around about 1 to 1. It starts to deviate from 1 to 1 as we get more and more mass, more and more protons in the nucleus. And the further away the further down the periodic table we get to the heavier elements, then we can see that that relationship deviates considerably from 1 to 1. We end up with a region up here which is around about 1.5 to 1. Notice it's quite broad. So 1.5 to 1 up in that region is not fixed. It's around about that. It's a rule of thumb. So if we plot the 1 to 1 ratio as a line, just draw a straight line through all the points, then we can see that it deviates quite considerably as the elements become heavier. And there's a couple of other bits of information on there which is incomplete, and so I don't particularly want to pay too much attention to it. But what it's describing is what happens when you get too far in one direction. You end up with some sort of radioactive decay taking place, whether it's the emission of energy and particles, or whether it's the other side of that line, it's the capture of particles to redress the balance inside the nucleus. these things can happen. And Graham will describe all this to you in a bit of detail later in the semester. Just to point out to you that not all things are equal, that other things need to be taken into consideration. We need to have a little bit of understanding about why particular nuclei are stable in order to understand a bit more about isotopes and the ratios in which they exist in the real world. So we can use that information. We can calculate that information for individual substances, elements, atoms. Then we can extend that further and calculate how much a mole of a particular substance will weigh. And to do that, it is not only just the sum of the atoms that make up that formula. So for water, H2O, it is the mass of 2 hydrogen atoms and the mass of 1 oxygen atom in grams summed together and give us the mass of 1 mole of water molecules. Straightforward, quite simple. Methane is the same, 1 carbon, 4 hydrogens. Added together, we end up with a number that we can weigh in grams, and we're confident, having weighed out that number of grams, that we will have Avogadro's number of molecules. Kind of tricky weighing out methane to gas, but water is pretty easy to weigh. So we should be able to do that. And any other substance that's easy to weigh, it's easy to do. For gases, we can do other things, but that's beyond the scope of this lecture. Maybe something I introduce you to next semester. Oh, that's bizarre. Okay, copper sulfate, the same applies. The reason I included copper sulfate into this is that when we are considering copper sulfate as a real-world substance, we have to take other things into consideration. Copper sulfate principally exists in 2 forms. It exists in this form here, where it's a crystalline solid made up of lattices of copper and sulfate ions intertwined, and the spaces in between these lattices are filled partially by water molecules. These water molecules are called water of crystallization. So if you were to try and prepare copper sulfate by evaporating a solution of copper sulfate, you would get blue crystals, and they would have a particular shape because of the geometry of the ions, and they would have water molecules trapped in them. So, on average, in a mass of copper sulfate, we find that for every copper sulfate molecule that is associated with it, 5 water molecules captured within the crystalline structure. And because you're weighing a real-life substance, then you have to take into consideration the fact that there is water in there and calculate that, factor that into your calculation for what you weigh out. Okay? So we can't ignore the water, we must add the water in. If it's written in the formula, it has to be incorporated into the calculation for the molar mass in this case. The calcium nitrate. The other thing to be aware of when you're calculating formula is the brackets. What's inside the brackets is a number of atoms. The number that follows the bracket is the number of these groups of atoms. So that has to be factored in as well. So calcium nitrate has 1 calcium, 2 nitrogens and 6 oxygen atoms in its formula. So close attention must be paid to all the components of the formula as it's written, so that we make sure we calculate the correct number of atoms to give us the correct molecular weight, formula mass. Okay? So, we know Avogadro's number, we know that it's universal, it describes 1 mole of a substance, and we know that we can relate the mass in grams to the concept of the mole. And we can also link the formula mass of that as well. And it's often the job of a practicing scientist to work out certain things from information. So you know how much a mole of a substance weighs, but you want some part of a mole or some multiple of a mole. How do you work it out? And for me, and I don't know if this helps you at all, it's certainly a little triangular relationship that I particularly like. It's applicable to a number of things where you have 3 components. So we can use that triangular relationship in a particular way, and we can calculate things from it. Providing we know 2 values, we can always calculate the third. So we can work out how much mass we require for a particular number of moles by multiplying that number of moles by a mass of 1 mole, and we end up with the mass we require for that number of moles. We can work out the number of moles we have in a particular mass of a substance by defining that mass by the formula mass, and that tells us what fraction or multiple of a mole we have of that substance. And if we don't know the formula mass, we can work it out based on our knowledge of how much we've got and how many moles it contains. So the relationship works in all three ways. We can calculate one of these parameters if we know the other two. Quite straightforward, but very, very important. If you're not familiar with this, then it's one of the things that you need to really get your head around. Okay? So that's fine, but what do we do with all this information then? Well, we can say some things about particular amounts. What can we say about 26.88 grams of oxygen molecules? We know that a mole of oxygen molecules weighs 31.99 grams, as close as can be to 32 grams. So we divide the mass we've got by the mass of one mole, and that tells us the number of moles of oxygen molecules we've got. And we can relate that to a real world number. We can say from that then, because we know that there's Avogadro's number of molecules in one mole, if we have a particular fraction or multiple of a mole, multiply that by Avogadro's number, and that tells us exactly how many oxygen molecules we've got. That in itself can be an important thing to work out. It might sound, why do I want to know the number of molecules? Well, a real world example of that is that my wife used to work for a small biotech company, and one of their lines of work was they were working with a protein called ferritin, which is a protein that's made up of multiple strands of peptides, and it formed naturally a cage-like arrangement, a globular cage-like arrangement. And what they discovered was that they could do things chemically outside of this protein and attach things to it that would react with other stuff. And it was an interesting concept, a well-known one. What they also did to try and make this a more desirable product for the marketplace was they were able to insert magnetic iron oxide particles into the cage of the protein, captured inside it, which made the whole thing magnetic. So they could then use that as a diagnostic and treatment tool in the medical world, because you could move things about the magnets. So they could target where they wanted these magnetic molecules with the reactive bits on the outsides to go, whether it was for a diagnostic tool to attach itself to something, a disease molecule. I don't know anything about biology, so I'm making this up. A disease molecule, is there such a thing as a disease molecule? I don't know. But it could be manipulated. It was a good way of manipulating these protein cages with the reactive stuff on the outside, was to put a magnet in the centre, and then you could use a stronger magnet and make them all move the way you wanted it to go. In order to do that, they needed to know how much iron to add specifically to get the right number of iron oxide molecules that fit nicely in the cage. So they had to do one laborious calculations of this height. So they know if they had X number of proteins, how many iron atoms and how many oxygen atoms do they need to actually have. And it wasn't in terms of moles, it was down to the molecular level. How many iron atoms do I need in my reaction? So these calculations aren't just trivial, I'm not just entertaining myself. There's real world applications for this that are very, very important. And we can say what we know about these things because we understand the relationship between the numbers. We understand the relationship between formula mass, and Avogadro's number. So we can work out pretty accurately how many things we've got so that they can react together in the right way. We can also say something about the 26.88 grams of oxygen molecules in terms of its constituent atoms. And this is an important thing as well, because we might often want to have a certain number of one type of atom. And the only way we can get it is by taking a formula that contains that atom and other atoms and other elements. So we can work out how many atoms of a particular element type there are in the formula. In this case, it's relatively straightforward. We know that there's two oxygen atoms in an oxygen molecule, and we know that each mole of oxygen atoms weighs about 16 grams. So we do the same thing. Our mass, 26.88, divided by the mass of one mole of oxygen atoms, tells us the number of moles of oxygen atoms we've got, and hence with Avogadro's number, how many actual oxygen atoms there are in 26.88 grams of oxygen molecules. So we're making all these relationships based on our knowledge of these concepts, and now we're introducing the idea of stoichiometry into it as well, knowing that each oxygen molecule contains two oxygen atoms. So quite a lot of, on the face of it, possibly complicated, possibly simplistic calculations, we can work out a great deal about something if we understand these concepts. Just to go over a few more things, how much sodium chloride must I weigh to get 6.23 moles? Work out the formula mass, multiply the formula mass by the number of moles, and we get grams. One thing I should point out to you, one thing I'm going to do with you later on, is this whole idea of dimensional analysis. Do you know what I mean by dimensional analysis? This is an example of dimensional analysis. We have one parameter with a particular unit to it, moles. We have another parameter with a different unit type, grams per mole. When we multipy these, or whatever we do to these two numbers, we do the same thing to the units. So multiplying moles by grams divided by moles, the moles cancel and our answer comes out in grams. One thing you will find with me, particularly students of physics, because we see you again in years, is that I am a stickler for units. I could have written that sometime with no units on it, and it would have been two numbers multiplied together to give another number, which would, to all intents and purposes, be meaningless. Because the number is just a number. If I didn't have the units there, what was I talking about? Bananas? Cow coins? Mice? Don't know until you put the units on. Then it has context in the real world. We know now that a number of moles multiplied by a figure which is expressed in grams per mole gives us an answer in grams. And it's vitally important that when you're writing down chemical equations, chemical formula, chemical calculations, that you include units. It may not be necessary to include them every single step of the way. For example, I haven't put grams beside the two numbers when I calculate the formula mass. But I have when I expressed it as the final value, because the final value has to be sensitive, has to represent the formula mass, grams per mole. So I'm going to pester the life out of your units. And you'll thank me for it. You will. You may not think so now, but you will. So, if we can do that for individual substances, then we can certainly do it when we come to slightly more complicated things, such as chemical reactions. So we have as our example hydrogen reacting with bromine to give hydrobromic acid, HBr. And as was true before, and it's still true, and will be true tomorrow, that the stoichiometric relationship between those three things in the chemical equation will not change. If we've written the balanced equation that accounts for all the atoms of all the substances there, then the stoichiometric relationship will not change. It will always be one hydrogen, one bromine to two hydrogen bromides. Yeah. We need to take this a little bit further now and look at ways in which we can apply these concepts in the real world. Because if you remember a few slides back, I talked about the reaction between sodium and chlorine. Provide sodium chloride. And I said that we can describe the physical state of substances as part of that process. So we can put a little S in brackets behind sodium to show it's a solid, a little G behind chlorine to show it's a gas, etc. And that has an impact, to a large extent, on how we actually go about performing a chemical reaction. Because it's not terribly efficient. It's dangerous to add chlorine gas to sodium metal. But they can't intimately mix it. One of the components is a solid, where reactivity can only take place at the surface, and the other is a gas that surrounds it. And the reactivity is not particularly suitable. It'll be dangerous, and it'll be inefficient and hard to do. And it's the same for any type of chemical reaction you want to do, where you want it to happen in a reasonable form and in a reasonable time scale. So one of the most important ways in which chemical reactions take place is that we carry them out in solutions. So we have one of our chemical reactants in a solution, we have another one in another solution, and we mix proportions of them together, and the chemical reaction takes place when the atoms stroke ions in one get in contact with the atoms stroke ions in the other. And the important thing here is that we need to have a way of measuring the concentration of the solutions we start with, so that we know that how much of each to react together. Because if we don't know the concentration, we don't know how much is there in total, and we don't know how much is there in any portion of that solution. So we're not sure how much of each to take and react together. Because it's not very efficient, it's arbitrarily throwing stuff together. because you end up with problems, you end up with impurities you might not want. If you're trying to make something that you want to extract from that solution afterwards and use, then you may have problems doing it. So we need to understand how we can relate the concentrations of things, or the stoichiometric amounts we need, to the concentrations of solutions. And we use this idea of molarity, and we have it as a fixed expression. We describe it as the number of moles of a solute, that's the thing you're dissolving in the liquid. It doesn't have to be solid, it can be a liquid itself. We call it a solute because it's the thing that's dissolving in our liquid, and we express it as that number of moles divided by 1 litre of solution, or that number of moles divided by 1,000 millilitres of solution, and we give it the units of moles per litre. And that's our concentration units for solutions of all types. Moles per litre. It's how we express them, moles per litre. So if we want to do some work here, we need to consider some things. We need to work out how much we want. If we want 1 litre of a 0.1 molar solution of sodium chloride, we want 0.1 of a mole in a litre. So we multiply our gram form of the mass, our mass of 1 mole of that substance, by the number of moles that we want, and that tells us the mass that we require. Then we weigh that out accurately, and we dissolve it in enough water to give a final volume of 1 litre. Now that's quite important. We don't dissolve it in a litre. We dissolve it in sufficient liquid so the final volume is a litre, because that sodium chloride is going to have a mass of its own. So it's going to occupy some space within the volume of 1 litre. So to add 1 litre to it means you've got the volume of a litre plus the volume of the salt. So you don't have a litre anymore, you've got something else. So we dissolve it in sufficient water so the final volume of the solution is 1 litre. And that's an important thing to remember as well. And what if we want a fraction of that volume? What if we want, in this case, 250 mils of 0.25 molar? We begin with the same way. We work out how much sodium chloride we weigh to give us 0.25 moles. And if we dissolved that in a litre, we'd have 0.25 molar solution. But we don't want that, we want a fraction of a litre. So the relationship between 250 mils and a litre is that 250 mils is a quarter of a litre. So our mass that we would weigh out for 0.25 moles is then divided by 4. So that mass, when dissolved in 250 mils, has the same proportion in moles of solute to solution that is still moles per litre. It's a quarter of a mole per quarter of a litre. Yeah, still with me? No surprises here? Anything you know already? Okay. So it's a matter of proportions, and we can scale up and down. It doesn't have to be as simplistic as take an amount, put it into a litre, and we have a solution of a particular molarity. So it's important to remember that the units are moles per litre. That does not necessarily describe the physical amounts that you've got. So 1 mole in 1 litre is 1 molar. 0.1 mole in a tenth of a litre is still 1 molar. 10 moles in 10 litres is still 1 molar. The ratio is the same, number of moles to number of litres. Yeah? So we can scale up and down and still retain the same basic information. That is, if I had a litre of the solution, it would contain that number of moles, the molarity. Useful things you can do with known molarity. So you can calculate how many moles are in a particular solution of known molarity. That's useful because if you want a particular number of moles, then if you know the solution's concentration, you know how much of that solution to get that gives you that number of moles. There are a number of ways of working this out. I have my favourite way of doing it, you may have your favourite way of doing it. It doesn't mean that I'm right and you're wrong, it doesn't mean that you're right and I'm wrong. My advice to you is, if you find a methodology for doing these calculations that suits you and you understand it, then use it, whatever it may be. But for me, this suits me. I want to know how many moles of sodium chloride and 50 mils of 1 molar. I know that 1 molar is 1 mole per litre, or 1 mole per 1,000 mils. I divide that by 1,000, that tells me how many moles is in 1 millilitre. And once I know how many moles is in 1 millilitre, I can work out very easily by multiplication the number of moles in any volume of that solution. It suits me. I find that an easy understandable calculation. It works for me every time. We can also calculate how much solution we need to provide us with a particular number of moles. So a particular volume solution, how much 0.1 mole of sodium chloride contains 3 moles of sodium chloride. So if we this time reverse the equation, we will divide 1,000 by the molarity. That then tells us the volume that contains 1 mole. And once we know the volume that contains 1 mole, again by simple multiplication, we can work out the volume that contains any number of moles. In this case, if we want 3 moles, then we have to have 30 litres of 0.1 mole of sodium chloride to provide that 3 moles. That's straightforward. I'm running out of time. I'll probably not finish this today. I'll maybe just do this slide and do that one as well. One of the most important things an analytical chemist can do is to use this notion of stoichiometry and moles to be able to work out how much of something is in a solution of unknown concentration, or how much solution you require to fully react with a particular volume of a solution of unknown concentration. In this case, how much of a solution of 0.2 mole of sodium hydroxide is required to fully react with 25 mils of 0.115 mole of HCl. So what we want to know is how many moles of hydrochloric acid is in that volume. And once we know the number of moles, and we understand the stoichiometric relationship between the two of them, we can then calculate how much solution we need to provide the correct number of moles. So if we divide our molarity of hydrochloric acid by 1,000, and multiply it by the volume we've got, that's telling us in the first step the number of moles in 1 millilitre, and we've got 25, so we discover we've got 2.88 times 10 minus 3 moles of hydrochloric acid. And we know the stoichiometric relationship is 1 to 1, so we know then that that is the number of moles we require of sodium hydroxide. So we use that second equation I showed you, 1,000 divided by molarity tells us the volume that contains 1 mole, multiplied by the number of moles we want, tells us the volume of solution we require. This is an important type of calculation. This is mostly associated with a thing we call titrometric analysis. Are you familiar with that phrase? Have you done titration before? You all have. So you're aware of the underlying principle, you're aware of the physical process of doing a titration. Graham's will talk to you a lot more about that in the next couple of weeks. Okay. Titrometric analysis allows us to calculate several things depending on what we're doing. The concentration of an unknown solution. It also allows us to calculate, if that's what we need to know, the volume required for a particular analysis, for a particular chemical reaction to go to completion. It requires us to have a balanced equation. It requires us to understand the stoichiometric relationship between the reactants. We're not so worried about the products here because they're going to happen anyway. We need to know the stoichiometric relationship between the two things that are reacting together. So we know our theoretical relationship between A and B is X and Y, X moles and Y moles. We know that the number of moles of A in our real example, the thing we do, is the molarity of the solution in moles per litre multiplied by the volume of the solution that we have, divided by 1,000. That tells us the number of moles we actually have. And the same for B, we work out in the same way. Molarity times volume divided by 1,000. Now it's those relationships, those mathematical or arithmetical equations, together with the stoichiometric relationship X and Y, that allows us to put it together in this format. So we can say that the stoichiometric theoretical relationship between X and Y, if we express it as X over Y, has got to be exactly the same as the real number of moles of A divided by the real number of moles of B. Yeah? So we're linking the stoichiometry to the actual experimentation. So we can write it in this way. And if we know several of these components, then we can calculate another one. And we can simplify it by taking the thousands out because they are common to both top and bottom line of that equation. So they cancel out, we don't need them. So it's the relationship of X and Y. The proportion of X to Y has got to be the same proportion as A to B in your real experiment. So if we have 10 mils of sulfuric acid at 0.1 molar concentration and you titrate it with 20 mils of sodium hydroxide solution, what's the concentration of sodium hydroxide? Well, that's our balanced equation, and we know stoichiometrically that one sulfuric acid from our equation reacts with 2 sodium hydroxides. So we can say then that the relationship, or the ratio 1 to 2, is equal to the moles of sulfuric acid we have in our reaction over the moles of sodium hydroxide we have in our reaction. We know the molarity of the sulfuric acid, Na, we know its volume, Va, we know the volume of sodium hydroxide, Vb. The only thing we don't know in that equation is Mb, the molarity of the sodium hydroxide. So we can rearrange it. Put them in, rearrange it. And when we rearrange it, we must incorporate the stoichiometric relationship into the calculation. So the number 2 on the bottom line in this equation has to be kept within the equation. It moves sign because we've rearranged to solve for Mb. But we must keep that stoichiometric relationship intact together with the real world information that we know. Okay? Not sure what's next. Oh, right. Just a brief summary of what we talked about so far. We talked about ions, how they're formed. Some elements lose electrons, some gain. They're paired reactions, one gains, one loses. Have to happen in tandem. We learned that covalent substances exist by a sharing of electrons between atoms of different elements, or the same elements. We showed how we can describe polyatomic ions. We learned about the necessity for properly balanced equations so that it gives us the correct information about a chemical reaction, and we learned the importance of the relationship between things in a chemical reaction, the stoichiometry. And we put these ideas together in conjunction with the idea of moles, formulas, formula masses, Avogadro's number, which allow us to work out things about the number of moles and the relationship between that and the mass of the substance, and allows us to carry out stoichiometric analysis. A real world experiment that allows you to work out the concentration. Okay, that'll be for today, I think, and we'll move on to Pastor's view next week.